So in Chapter 18 now, Dr. Baumeister's Physics 2 class, studying the thermal properties of matter, and we want to look at an application of the ideal gas law, the equation of state for an ideal gas. PV equals nRT, in the kinetic molecular model of an ideal gas. From this ideal gas law in this model, we have that the kinetic energy of a particle, rather its translational kinetic energy, is 3/2 nRT, from which we can then get the velocity, the average velocity anyway, to be 3/2 k t, and from that the root mean square, a measure of the speed, the root mean square, that is, the root of the mean, being the average of the square of the velocity, we find in this model to be 3 kt over m, square root, where m is the mass of a single particle, and we use this result, in this model, to answer this problem 1831 here. A deuteron is the nucleus of a hydrogen isotope and consists of one proton and one neutron. The plasma of neutrons in a nuclear fusion reactor must be heated to about this given. So we have this temperature. This velocity, I should have pointed out, depends on the temperature and the mass. The greater the temperature, the hotter the gas, the faster the particles. We'd expect that. And the heavier the particle, this m in the denominator, the slower the velocity. So it's intuitively correct. We want to find the root mean square speed of the deuterons. We will just answer part A. This is the root mean square speed, so to answer this question we will need temperature and the mass of a single particle, a single deuteron. Since we have the temperature there, what is the mass of a single deuteron? We have that the molar mass is equal to Avogadro's number times the mass of each particle. So that the mass of each particle then will be the molar mass divided by Avogadro's number. The molar mass you can get from the periodic table. It's in grams per mole of single atom molecules. For the present case, what is the mass of a deuteron? It's really just the mass of two hydrogen atoms. You can ignore the mass of the electron since it's negligible here. So that's what we really want to use for this molar mass. What else do we need here? Oh, it will be two of those. So let's just solve then for the root mean square (3 kt). Yeah, that's the other thing I wanted to say, that the Boltzmann constant, to save us a little algebra here, is the gas constant divided by Avogadro's number. So the Avogadros will cancel out. What is that? Yes, and then this. Those do cancel out. And what is this, finally? Just a little bit of cleaning. Three times the number they give for the temperature. This, for the gas constant. There. And the mass from the periodic table, 1.008, in grams. So we need to make that kilograms, and use this conversion factor to the 1/2. Putting that all in 9 times 8.31 times 10 to the 11 to the 1/2, sorry, and that is about 1.9 times 10 to the 6. There. Should be about right.